Okay, so problem 15 gives us this fun little graph here. It says it consists of four semicircles, and it defines g of x as the integral from 0 to x of f of t dt. And they want to know, where is g of x non-negative? So where is g of x either 0 or positive? This is considered an accumulation function, excuse me, because as x increases, you're kind of accumulating more area or more y values for that matter. Anyway, so let's do the more straightforward piece of it, which would be, I'd say, the right half of the graph. And maybe before we get started, let's just talk about, if you did integrals from left to right, what kind of values would we get for different pieces? So keep in mind, integrals from left to right. So if we were to integrate from 3 to -2 for this function, since the graph is above the x-axis, we would get a positive value. If we were to integrate from -2 to 0, we would get a negative value. From 0 to 2, a positive value. And then from 2 to 3, a negative value. Okay, and I don't think this is anything new at all. This problem does have a little bit of a spin on it, but it's not a big deal. Okay, so let's kind of play around with x values. Let's say you start at 0. So if x was 0 and your lower bound is 0, then your value for this whole integral would be 0. So I would include 0 in whatever answer you choose, because g of x would be non-negative when x is 0. Now, what will happen if we slide x, to the right a little bit and just keep moving x to the right? Well, what is it that you're accumulating? You're accumulating lots of positive stuff. And so if you keep sliding x to the right, you just keep accumulating more positive stuff. Until you get to 2, then you do start accumulating some negative stuff, but it's not enough to cancel out the positive amount that we had accumulated. So I would claim your answer should include the interval from 0 to 3. Okay, now let's talk about the trickier side, the part where we have to kind of go to the left. And I do want, and this is something we haven't played around with a lot because we haven't really needed it, but we did mention it briefly at least one point, so I do get to say recall. If you have the integral from a to b of a function, let's talk about what happens if you were to switch the bounds. So according to the fundamental theorem of calculus, this would equal big F of b minus big F of a. And then if I wanted, I could rewrite that as the opposite of f of a plus f of b. I could factor that out, the negative out. And then I could rewrite this in integral notation. So this piece would be the integral of f of x dx. And your upper bound would have been a, your lower bound would have been b, but you notice you have the opposite right there. So this is the point that I'm about to be using. If you were to switch the bounds on an integral, you get the opposite of what you would have had before. So with that said, since for this problem, the lower bound has to be 0, if you start moving to the left, then you'd be doing, for example, like if you're looking at this piece right here, the way this, that would be like, what's g of -1? What would be the integral from 0 to -1 of f of t dt? Notice that we would have said that this would have had a negative value, but that's if you're moving from left to right. If you're moving from right to left, that would be like switching the bounds. And so you'd get the opposite of what you would have gotten. So, so the point is this: when your x values, you start playing around with x values that grow and get more and more negative, you're going right to left. So you would be not accumulating negative things here. You'd be accumulating positive values because you're going right to left. And then you would be accumulating some negative stuff, but not enough negative stuff to cancel out the positive amount you had accumulated. So for that reason, g of x would be non-negative for all the x values, with x goes from 0 to 3, or if x goes from 0 to negative 3. The correct answer is A. Okay. Hopefully that makes sense. If not, feel free to contact me and I can always do a redo on the video. So I also wanted to look at problem 17 in this video. It says a rectangle with one side on the x-axis has its upper vertices on the graph of y equals cosine x as shown in the figure above. What is the minimum area of the shaded region? For this problem, there are so many ways to go about it. I have a way that I like, and then you're welcome to have your own way. As long as we get the answer B, it's probably fine. So for this problem, I decided, okay, well, what is it I want to do? So I'll write it up here. I want to, it says minimize area of shaded region, right? Well, you're going to end up with kind of a complicated function rule to work with if you're going to be really straightforward with this problem. It's doable, but it's more time consuming than you'd probably prefer. So another way to minimize the area of the shaded region would be to maximize the area of the rectangle, since the outer region here is kind of fixed. So I'm just going to say AKA minimize area. Whoops, when I say minimize, I don't mean that. It'd be the same as maximizing the area of the non-shaded region. So that's what I decided to do, is I decided to figure out what's a formula for the area of that rectangle, which is relatively simple, and then I just figured out, well, what's the maximum area of that rectangle? So I'll just say area of rectangle. So if this is the point xy, then the area would be 2x times y. And then you're going to need this in terms of one variable. So all in terms of x, it'd be 2 times x. And then what makes that y so special is it has to be on the cosine graph. There you go. And then there are lots of ways to handle this situation. You could take the derivative and find when the derivative is 0 and do all sorts of fun calculus. Or you could figure that since you are on the calculus section, on the calculator section, you could really take advantage of that. And so what I decided to do was just go ahead and graph the area function itself. Make sure you change your window. I changed it to be from 0 to, this is pi divided by 2. I hope that makes sense, that value would be pi over 2. And then for the y coordinates, I just did let zoom fit do its magic. So this is the graph of the area of that rectangle. And I can see the area growing, and I can see the area getting to its maximum value, and then the area decreasing. And so let's figure out what the maximum value of that area of the rectangle is. So if we do calculate maximum left bound, right bound, and have it calculate it, what we found out, I'll just sketch a little picture here. Is that the actual maximum area of the rectangle is this amount right here. So max area of the rectangle. You know, is that right there. Okay, so now though, let's make sure we answer the question. They said they wanted us to actually minimize the area of the shaded region. So I know the maximum area of this, that's this number right here, but I actually need to know the, the area of the shaded region while the area of the rectangle is this number. So to do that, I'll just do the integral from negative pi over 2 to pi over 2 of cosine of x dx. I hope it makes sense. That's negative pi over 2 and that's pi over 2. And then I'm just going to subtract off. There you go. Okay, so let's see. Okay, so the area of the shaded region would have been, if it wasn't for the rectangle, would have been 2. And then we're just going to take off that maximum area that we got there. There we go. We got 0.877, 0.8778 that is, which matches up with B. All right, I hope this helps you guys. Take care, everybody.